Welcome to another exciting educational content video brought to you by Chrysolite Tutors. We're looking at Physics 124. Title of the course is Geometric and Wave Optics. Unit 2, we're looking at Unit 2, Reflection at Curved Surfaces. Recall that Unit 1, we looked at plane mirror, that's reflection of light in plane surfaces. So we're taking it up a step further to see how rays and beams of light behave on curved materials. So by way of objective, we'll see images formed in a curved mirror. We'll look at images formed by a concave mirror when the object is placed beyond the center of curvature. Image formed by a concave mirror when the object is placed between the center of curvature and the principal focus. And we'll look at images formed on the concave mirror when the object is placed before the principal focus. The mirror formula, magnification, conclusion, and the TMA. So we'll dive in to the structure of a concave and a convex mirror. So look at how it looks like. This is a concave mirror, and you know the mirror is like a bent glass, so I can just put a thickness here. This bent glass has a the glass side and the coated side. The coated side is the side that absorbs reflection, that absorbs rays so that it does not go in. So you have the refractive side. The refractive side is this place, refractive side. This is refractive, nano reflective, because we're looking at reflection. Reflective side and the coated side. This is the coated side, coated with silver lining. Okay, so this is a concave mirror, or you can call it a converging mirror. Why are we calling it converging? Because any image, any ray that is incident on it converges at a point. I will discuss that later. That's why you are having it as converging mirror or concave mirror. Concave because the reflective side is curved in. The reflective side is curved inwards. Now, this is for the concave or converging mirror. So for the diverging or convex mirror, this is the glass side bulging out, and the coated side is curved in. So this is the reflective side. The reflective side is curved out. Reflective side, this is where the incident ray is coming to, and the coated side is curved in. The coated side, where you have the what's it called, the silver lining. So this one is called a convex mirror or a diverging mirror. Diverging in the sense that rays of light that incident on it will diverge after reflection. So we're going to look at this. We're going to, by way of objective, we're going to distinguish between the reflection on the curved surfaces, identify principal focus. We'll also look at images formed in a curved mirror using ray diagrams. State the mirror formula. Like I said, apply the mirror formula to obtain image distance or object distance. So stay tuned again as we dive in. All right, so let me take this off and let's see what happens to images that are incident on a concave mirror. So I will just start and identify the parts of a concave mirror. So this is a concave mirror, like I said. The coated side is at the back, and the reflective side is at the front. So if I have a concave mirror like this, there's an imaginary line that cuts the mirror into two. This imaginary line is used for analysis. We call this line the principal axis. This line is called the principal axis. The principal axis. By the way, this is a concave mirror, or you can call it the converging mirror. Okay, so I will explain why it's called converging. Okay, so there's an imaginary line that tells us the principal axis. Okay, so there is a point at this part of the mirror where this imaginary line cuts the mirror. I will call this part the pole. The pole is called the pole. P, called P, pole. So I can come here and define this so that P is equals to the pole. It's called the pole. So the pole is just the center part of the mirror when divided into two by the principal axis. Now there's a point from distance between that point to the center or the pole. We call it R. We call it R. And that R, okay, let me don't call it R. Let me call it F first. F. That F is called the principal focus. The principal focus. The principal focus, or just simply focus. Let's call it focus. F, focus. Now, focus is the point where images that are reflected from this mirror converge at. That is why it's called converging mirror. So it converges when it's reflected. It converges here. Understand? There's another point again. They're called R. We call it R, or radius of curvature. Radius of curvature. So radius of curvature is R. R. So there's a relationship, at least a mathematical relationship between F and R. R is equals to 2F, or F is equals to R over 2. So F is the focal length, or the principal focus. The distance between this point, principal focus, and the mirror is called the focal length. Focal length. This focal length is actually a constant. It can be determined. That's for the material. For the particular mirror, it can be determined. Understand? It can be determined. And the distance between this and this is called the radius of curvature. Radius of curvature is, they are all measured in length, in meters or cm, or of course in cm. I can be converted to meters if you want to. Okay, so we'll look at other parameters or other attributes of these things I've defined. I've defined the principal focus, I've defined the pole, the principal axis, the focus, and the radius of curvature. So there are 2 points that a ray of light will pass through. Either pass through the center of curvature or pass through the radius of curvature. So we're going to be looking at ray diagrams. Okay. Now, let me bring up some particular scenarios and explain how the ray diagram will work. Okay, so I'm going to be explaining some attributes, different positions where you place the object on the mirror, on the concave mirror, and the kind of image that is formed. Recall when we did unit 1, we said that for plane mirrors, the image placed before the object placed before the plane mirror forms image that is the same size as the mirror, forms image that is upright, forms image that is laterally inverted, that is left-right orientation. Then is virtual. Okay, so but that is just for plane mirror, and that 4 characteristics of image form is just fundamental. Nothing changes. Not even if you change the distance of the mirror of the object. Now for curved mirrors, especially for the concave mirror, first of all, we'll see that the nature and the feature of the image that is formed varies depending on the position it is placed. Now this is a concave mirror. I said there's a part of it, an imaginary part that is called the principal axis, and I have a C or R radius of curvature. Let me call it C. Then this is F, and this is P. You can either call it R or C. You can define it. R C here is the radius of curvature. Okay. Now, if I have that my object is placed beyond C, object placed beyond C, not beyond C, the musician, but beyond C, this particular C. Now the object is placed beyond C like this, standing upright, placed beyond C. First of all, I will take a ray coming from the tip of the object like this. Like I said in the first unit, that every object radiates, have rays coming out from every particle of the object. But for optics, we just simply minimize the number of rays so that we don't complicate our analysis. So the ray from the tip of the object hits the mirror, and it's reflected through the radius of curvature, the focal length. Reflection, it goes through the focal length, and at the same time, this second ray comes through the center of curvature like this, and also reflects back. It hits the mirror somewhere, wherever the mirror extends to. It hits the mirror and reflects back. So where they meet, where this first ray that is reflected through the focal length or focal point, and the second ray that goes through the center of curvature hits the mirror and go back to the center of curvature, where they meet, they form an image upside down. So what is the nature of this image that is formed? I will put the thing here. I hope you can see. Nature of image formed. We just say nature, that image form. First of all, is diminished. Image form is diminished. What's diminished? It's smaller in size than the object, this image. Smaller in size. Object O, image I, smaller in size. Understand? It is inverted. Inverted means that it's upside down. It is real. Real because it is formed before the mirror. If it is formed behind the mirror, then it is virtual. Understand? It is diminished, it is inverted, it is real. It is real. Okay, what else? What else? Okay, it is formed between C and F. Formed between C and F. Formed between C and F. So these are the features of this particular configuration. Object placed beyond C. Now I have another positioning. This is the mirror, curved mirror. This is the curved mirror, and this is the principal axis. Okay, so if I have my pole here, P, I have my focal length, F, I have my radius of curvature, C. If I place the object on C, so the what we are looking at is objects placed on C, object placed on C. So the first ray from the object, this object O, goes and hits the mirror, and normally is reflected through F. Second one too goes through F, hits the mirror, and is reflected back to this point, and the image is formed like this. So this object is image. If you check the configuration or check the nature of the image formed, nature. So remember, when I put nature here, I mean the nature of the image formed. One is same size as the object, not diminished, same size. So these and these are the same size. So they might ask you, what's the nature of the image formed when an object is placed on C before a concave mirror? So you say number one is same size. Number two, it is inverted again, upside down, inverted. Number three, it is real. Why is it real? It is formed before the mirror, and the position of where it's formed, it is formed on C. Formed on C. Okay, so this is the nature of image placed that is formed when the object is placed on C. Another one is when we now place the object between C and F. So I'll come here, I'll draw my mirror, sorry, my principal axis, the mirror, curved mirror like this. Okay, so I have C, F, and P. So objects, okay, I won't have where I put my nature. Let me just come somewhere here so that I can have where I can put my nature. Okay, so this is the principal axis. This is C, F, and P. So object is placed between P and C and F, these objects. So so I go again. Ray hits the mirror, reflected through F. Same time, this one hits the mirror again, and it's reflected through. Wow. Okay. I may not have space, so let me redraw the diagram. What I'm going to do now, there will not be space for it. Okay. Okay. Let me take this off so that you can understand it. Okay. So I am on the configuration where the object is placed between C and F. Let me make it bigger so that you can understand. So this is P, F, and C. So object is placed between C and F. So first of all, the incident ray from the top hits the mirror and reflected through F. This is F. And at the same time, this one also hits the mirror and reflected back through C. Okay. Actually, it's going to form, this is how it is, please. It's going to form, I'm trying to, because it's not drawn to scale, but normally this is what happens. The two rays here will meet somewhere here. Will meet somewhere here. Pardon my drawing. This is it. Okay, so this is it. So what is this? This is objects placed between C and F, between rate of curvature and the focal length. So what are the nature of the objects, the image form? Number one, image is magnified. Nature of image form. So this is where we get magnified image. Nature of image formed. Image formed. Okay, so number one, image is magnified. See, magnification means that the image is bigger than the object by far. Image is magnified. Magnified. It is still inverted. Inverted means it's upside down. It is real. Why? Because it is at the same side of the object with the mirror. Okay, and finally it is formed beyond C. Formed beyond C. Formed beyond, not beyond C. Beyond C. Formed beyond C. Okay, so that is for object placed between C and F. Now, if we now have the object, see the object has been moving from beyond C to C and now between C and F. What if you now have the object placed on F? What happens? So let's see that quickly. Let's see that quickly. You can pause the video always to see what is written and understand. Just you can pause the video. Okay, so the object is now placed on F. So this is the principal axis. This is C, F, and P. Object is placed on F. What happens? So I have the ray hits here like this and goes through like this, refracted. The ray goes up, hits here, and refracted. But in this case, unfortunately, the ray will not meet. There are two parallel lines. The reflected ray coming from the that is passing through F focus, and the reflected ray also passing through C. In this configuration will never meet. This is object placed on F. Object placed on F. Now, when I was studying, when I was doing this course, what I just know is that once it is placed on F, it is infinity. This is infinity. F and infinity. Infinity has F in it. So, but if you know the diagram, you always know that these two rays will never meet. By scale, even if you draw by scale, it will never meet. So any reflection through F and reflections through C in this configuration will result to image formed at infinity. So the nature of image formed, number one, formed at infinity. Formed at infinity. Infinito. Secondly, it is magnified. Very, very magnified. third, it is real and formed, okay, yes, formed beyond C, formed at infinity. Okay, it's inverted, sorry, inverted. Okay, so these are the characteristics for image that is placed between on F, directly on F. So it is real, it is real, it is real, it is formed at infinity, it is inverted, and what have you. And finally, if I now place the objects between F and the pole, what happens? If I form the object between F and the pole, what happens? So we're going to see that quickly. Object between F and the pole. This is the concave mirror. This is the line, the principal axis. This is F, and this pole, this is C. So if it's placed like this, so it hits the mirror and refracts here, and this one hits the mirror and reflects here. But at this point, the rays are diverging, that they are just going separate this way. They will not meet, they will not be parallel. But something happens if you extend this ray, this one that is reflected through the F, to the focus. If you extend it this way, backwards, into at the back of the mirror, and extend the one that's reflected through the curvature, rays of curvature, they will meet at a point virtually, and when they meet at this point, they form a virtual image behind the mirror for the first time. Wow, we're seeing. Okay, so this configuration is what? Object placed between F and P. So it is formed behind the mirror. What is the nature of the image formed behind the mirror? The nature of image formed. Number one, it is magnified. Magnified, bigger than the object. Magnified. Number two, it's upright. See, everything now is going the other way. It's upright, then it's virtual. You see, at this point where the object is placed between F and P, everything turns the other way. It is virtual, upright, it is magnified. And what else? It is formed behind the mirror. Formed behind the mirror. Formed behind the mirror. Okay, so as a rule of thumb, anytime you see broken images like this or images formed behind the mirror, it is virtual. It is virtual. But if it's formed on the same side of the mirror with the object, the same side of the object, as regarding the mirror, it is real. That's another thing you need to know. Okay. So that's for that. So we have the mirror formula. It has been proven mathematically in the lab. There's a course, practical physics, where you do the practical to this particular topic. We determine in the lab the mirror formula. Mirror formula states that 1 over V, let me put it on the board like this. Mirror formula. It states that 1 over V plus 1 over U is equals to 1 over F. Okay, so where V is image distance. What's image? Image is what is formed after the object is being reflected. That's what image is. So image distance. Distance from where? Distance between the image and the mirror. Okay. U is equals to object distance. And F is equals to the focal length of the mirror. This will also be given. This is like a constant for each mirror, or it can be determined if you have these two parameters. In the lab, actually, there's a experiment that shows this. This is 1 over U axis and 1 over F axis, 1 over V axis, and this point is the focal length. Here to get focal length, it's determined in the lab. So that's not the focus for this particular course. We are looking at mirror characteristics of curved mirror and mirror formula. Then we'll kind up with magnification. So what is magnification? magnification is actually the ratio. Magnification is the ratio between the image size / distance to object size or distance. Any two can be used to compute magnification. So it is denoted by M is equals to VD, V subscript D over U subscript D, or V subscript S over U subscript S. Don't mind my subscription that I'm doing here. I'm writing it this way so that you can know what you are comparing. If you are comparing distance, it is image distance and object distance. If you are comparing size, it is image size and object size. So magnification is actually without any units because it is a ratio of two lengths. So it is a number that you get. It's just a ratio between the length or the size of both image to object, image to object. So that is what magnification is. So we'll look at practical examples. We'll look at some calculations. So stay tuned. If at this point you're not subscribed to our channel, kindly subscribe so I can get more of our content. Okay, so I have on the board said an object is placed 0.15 meter in front of a concave mirror of focal length 0.1 meter. Determine the position, nature, and magnification of the object. So the mirror formula, quickly, this mirror formula. So we have 1 over U plus 1 over V is equals to 1 over F. So we are given object distance U as what? 0.15 meters, and we are given focal length F as 0.1, or to look for V. So I can put it here, 1 over 0.15 plus 1 over V is unknown, plus 1 over F is 0.1. So at this point, I'm going to quickly multiply each term by the product of these two. At this point, it's just mathematics. There are different ways you can solve it. I can decide to come here and just do like this, okay, to collect like terms. So 1 over V at this side is equals to 1 over 0.1 minus 1 over 0.15. This is a fraction, this is a decimal that can turn to a fraction. Already 1 over V is the same thing as saying this is 1 over 0.1 is the same thing as saying 1 over 10. And 0.15 is the same thing as saying 50 over 100. Over 100. Very good. So 1 over V is the same thing as saying this one will become 10 minus 100 over 15. Okay, so at this point I will just do the maths. It's 1 over V is equals to square. The LCM of these two is 15, and this is 150. That's 1 into 15 is 15, and 15 times 10 is 150 minus 15 into 15 is 1. 1 times 100 is 100. So 1 over V is the same thing as saying 50. 150 minus 100, I will have 50 over 15. So this can now be V is equals to 15 over 50. Okay, so let me wrap up here. So V is equals to 15 over 50. 15 over 50. So in the same thing as saying 1.5 over 5, and the same thing as saying 0.3. So V is 0.3 meters. So if I've gotten V, M is V over U. Remember, M is equals to V is 0.3 that I've gotten over u. What is u from the question? U from the question is what? 0.15, 0.15. Okay, so you know normally when my position 0.3 over 0.15, this goes like this goes like this. So I have 30 over 15, which is 2. So if my position is 2, it means that the object increased. Positive value for m means that the object increased. So determine the position of the position. The image is 0.3 or from the mirror. Is 0.3 from the mirror. It increased. It increased. The only time that there's an increase is when the object is formed beyond C. And it's real. And it's real. So for a concave mirror, if the object is magnified, it is formed beyond C. It's inverted. I've got the particular the length of this distance that it is formed from the mirror. So that just answered the question. I've got this parameter. This one shows where it is formed from the mirror. It's formed 0.3 meters from the mirror. This one shows the nature that it is magnified. Okay, so we'll do one more example and wrap up this video. Okay, so we have on the board second example. It says a man has a concave mirror with focal length of 40 cm. How far should the mirror be held from his face in order to give an image of twofold magnification? This last statement here, twofold magnification, is just this relationship. M is equals to V over U. 2 is equals to V over U. That means the magnification is twofold. So this is the first question I'm going to use. From here, I can get that V is equals to 2U from here, because 2 multiply this U and V remain. I'm just cross multiply. So I've gotten this relationship. This is from magnification. Understand? Now mirror formula. Okay, we are given from the question. We are given that focal length F is equals to 40 cm. We don't have U, and we have V as 2U. Understand? And what we are to look for is U. They said, how far should the mirror be held in front of him? So that's how far is the distance between the man himself and the mirror. The man is the object. Sure. And the image is formed by the man's object on the mirror. So this is what we have. And to calculate it, we just say 1 over U plus 1 over V is equals to 1 over F. U is what we're looking for. 1 over U is unknown, but V is given as 2U from here, 2U. And F is 1 over 40. That is 1 over F, so 1 over F is 40. So this is good to go. We can find the LCM. These things are common. LCM of this and this is, okay, let me use another method. Okay, LCM can go. This is 2U. LCM is 2U. That is what is common between these two of them is 2U. U into 2U, that is 2U divided by U, will give us 2. That is cancel. So I have 2 as remaining here as a factor. That is U into 2U is 2. 2 times 1 is 2. Plus 2U into 2U is 1. 1 times 1 is 1. So it's equals to 1 over 40. 2 plus 1 upstairs is 3 over 2U is equals to 1 over 40. All right, so we'll cross multiply. This multiply this. So I have 2U is equals to 3 times 40 is 120. So U is equals to 120 over 2, which is equals to 60 cm. So the man will place the mirror 60 cm away from his face for him to be able to get that magnification of twofold. So that answer is simple enough. Let's continue with what we have. This particular course, we'll be wrapping up with convex mirror. So convex mirror, we have seen concave mirror in a detail, but convex is just one particular way it is showing us the image. It doesn't go beyond that way. So the convex mirror is drawn like this. Like I said, the reflecting side is curved outwards, and the coated side is curved inwards for convex mirror. This is convex mirror. Convex mirror, or what do you call it again? Diverging mirror. Call it convex or diverging mirror. Okay, so this is how it is. So we have our principal axis like this. So for convex mirror, the pole is here and every other thing is inwards. So I have the focal length or focus here and the radius of curvature here. So anywhere you place the object in front of the mirror, understand? The thing is that the ray from here hits the mirror like this and it reflects. So the reflection is divergent. Understand? So the first ray appears to be coming from the focus. Yeah? Okay. And the second one here hits this mirror, still reflects, but appears to be coming from the center of curvature, or radius of curvature. So here, the image is formed here, and the nature of this image formed by a diverging mirror is, number one, it is diminished, small size, diminished, so that means magnification is less than 1. Number two, it is upright, always upright. Number three, it is virtual. Why? Behind the mirror. Okay. Number four, it is always formed between P and F. Formed between P and F. Formed between P and F. P is what? Pole. F is focus. Focus. Okay, so formed behind the mirror, always virtual, upright, diminished, and smaller than the mirror. So diverging mirror is very easy. The same formula for mirror formula applies for diverging mirror. So if you have a question that has to do with diverging mirror, apply the same principle and you are good to go. So we have looked at the curved mirror, reflection on the curved surfaces. We saw the different configuration for concave mirror and the convex mirror. You can understand what a principal axis is, the focal point, the radius of curvature, and the various object placed at various points on the principal axis, how it behaves for concave mirror, and how it behaves for convex mirror. And you've seen the mirror formula and the magnification formula. So I hope this video has been informative for you. I'd like to thank you for viewing.